Kia ora tātou. My name's Diane Kenwright. I'm a pathologist with Awanui Laboratories and with the University of Otago, Wellington. Today, I'm going to talk to you about new insights in endometrial carcinoma. Today, I'm going to talk about the New Zealand context of endometrial carcinoma, the traditional classification of endometrial carcinoma, the new classification, and how we're going to put all this together in laboratory workflows. Endometrial cancer is increasing rapidly in New Zealand, a 59% increase in cases over the last 10 years, particularly in Pacific peoples, and particularly in high-weight individuals. Notably, it has been also increasing in younger age groups. The good news is that more people are surviving endometrial carcinoma. What are current health professionals' concerns about endometrial carcinoma? They are concerned about the disproportionate way that endometrial carcinoma is affecting Pacific women. They say things like, we're probably seeing more younger women than we were. In the under 45s, 47 to 48% of them are Pacific, and the BMIs range up to about 90. They say, I know we're seeing an increase in incidence of endometrial carcinoma in younger women due to the obesity epidemic. There's a huge amount of alarm in the oncology community about the rates of endometrial cancer. They see other rates staying the same or going down, but endometrial carcinoma is an outlier where our rates are increasing. Let's have a look at some of these graphs. So they are from a paper that was published about in 2020, looking at people in the South Auckland area with endometrial carcinoma. So the first thing to do is look at this graph here, where we notice that the rate is steadily increasing in endometrial carcinoma, and it's particularly increasing in the Pacific population. We also note that while most endometrial carcinomas will occur between 50 and 70 years, there is a significant number that occur at age less than 40 years, and most of those are in the Pacific community. When we look at body mass index and endometrial carcinoma, we will see the most significant load is in those who have a body mass index of more than 40. And again, Pacific people are disproportionately affected. So what causes endometrial carcinoma? The traditional classification developed in the 1980s divided endometrial carcinoma into type 1, which was endometrioid type, and was driven by estrogen. This makes up 85% of all endometrial carcinomas. We grade it from 1 to 3. And we can see in this graph here that it really does make up most of the cancers that we see. But there is a small proportion, 15%, which we call type 2. And that is non-estrogen driven, and mainly is composed of serous type and clear cell type endometrial carcinomas. So type 1 is due to excess estrogen. Where does this excess estrogen come from? Well, the most important place that excess estrogen comes from is adipose tissue. Precursors for estrogen are made by the adrenals and then converted to estrogen in the adipose tissue. So if a person has more adipose tissue, then they will have more estrogen. Some other places that excess estrogen can come from are tamoxifen. So tamoxifen is a drug that's used in the treatment of breast cancer and can stimulate endometrial growth because in the endometrium, it acts like estrogen. Older forms of hormone replacement therapy used to have unopposed estrogen, but we don't use those anymore. And then there's anovulation. So this is where the menstrual cycles, particularly around menopause, result in development of a follicle, which produces estrogen, but this doesn't mature and produce progesterone, and so we get excess estrogen. But the big message is type 1 endometrial carcinoma is due to excess estrogen. When we have excess estrogen acting on the endometrium, it goes through a series of sequential developments. At the left-hand side here, we have normal proliferative phase endometrium. At the start, unopposed estrogen, excess estrogen, leads to disordered proliferative phase. The cells are a bit big and funny looking, but the glands are a bit big and funny looking, but there aren't too many of them. And then, if we continue with unopposed estrogen, we get hyperplasia where the glands become more crowded. Eventually, continued estrogen exposure results in the accumulation of mutations in the proliferating glands, and we get hyperplasia with atypia, finally ending up in endometrioid adenocarcinoma. Progesterone is protective in this process. So in normal menstrual cycles, progesterone in the second half of the cycle will halt the proliferation of endometrial epithelial cells. And then, of course, it sheds. Similarly, exogenous progesterone that's either taken orally or present in an intrauterine device like a Mirena, will cause the epithelium to stop proliferating. So this is an endometrium here that has been exposed to a Mirena, and the glands are no longer kind of lush looking, lined by proliferating cells. They've all been switched off, and these glands are thin and atrophic. So progesterone is protective against endometrial cancer. So we've been talking now about type 1 endometrial cancers, where normal endometrial glandular epithelium through excess estrogen goes through a series of changes, which ends up with it being low-grade endometrioid carcinoma. What we're going to think about now is the other 15%, the type 2 endometrial tumours. So they are estrogen independent, and they usually begin with a mutation, particularly a p53 mutation in a cell in the endometrial epithelium. And this gives rise to serous endometrial intraepithelial carcinoma and then invasive serous endometrial cancer. Clear cell tumours also have a high rate of p53 mutations. The difference between type 1 versus type 2 cancer isn't just in how it forms, it's in how it behaves. Type 1 cancers, which are endometrioid, do much better than type 2 cancers, both for recurrence-free survival and distant metastasis-free survival. In other words, if it's a type 1 cancer, the woman has a much higher chance of being cured and living a long life. Whereas clear cell and serous, the type 2 cancers, have a much, much worse outcome. In 2013, there was a paper published looking at the genomics of endometrial cancer, and it came up with some startling findings. These were developed over the next 5 years and ended up in a case series where cancers were looked at as part of cancer's molecular characteristics were looked at, and that was compared to their outcomes. What these showed was that the genes that were switched on in the cancers played a large part in determining the outcomes. There were 4 distinct groups that were identified. The P53 abnormal group, which did very badly. The mismatch repair deficient group, which was an intermediate group with the no specific molecular signature group. And then this group here, Pol E, which did amazingly well. People with Pol E mutations did not die from endometrial cancer. So what's new and surprising about this molecular classification? Let's think about P53. What's not surprising is that P53 cancers do badly, because we already know that P53 cancers includes all the serous cancers, and they are all P53 mutant on immunohistochemistry. What is new and surprising is that endometrioid type 1 cancers that are P53 mutated also do badly. They switch into the bad actor group. And clear cell carcinomas that are P53 mutated do even worse than usual. So the practical outcome is that all P53 mutated cancers should be treated as high-risk cancers, even if they look low-grade. The lab effect is that all endometrial cancers should get a P53 immunohistochemistry. And in most labs in the country, doing a P53 on the curettings of endometrial cancer is now routine. And that's to identify these bad P53 cancers that aren't serous. DNA mismatch repair. Remember, this group has an intermediate outcome. What's not surprising is that these DNA mismatch repair abnormal cancers are mostly endometrioid type 1 cancers. What was new and surprising is that these cancers do worse than the no special type, no special mutation type cancers. So we can separate those out. Practically, they respond differently to chemotherapy than other cancers, and this can be targeted. We were already doing DNA mismatch repair on endometrial cancers, the MLH1, PMS2, MSH6, MSH2, because we were looking for Lynch syndrome. So this has no effect on our lab work, even though it's now being interpreted in a different way by the clinicians. Pol E. Now, this is the most important and most new and surprising thing that has come out of this research. So, Pol E cancers do really well, even though they look terrible and can be P53 mutated. The picture here shows a terrible cancer, but because this is Pol E mutated, this person will do surprisingly well and will not die of their cancer. What is Pol E? So Pol E stands for DNA polymerase epsilon. These are the DNA polymerases. And what happens is they work here at what's called the replication fork, where DNA splits and then new bases are added as it replicates. It builds the DNA during replication, but most importantly, it also proofreads it. What I'm going to do now is show you this film so that you can see how it might work in real life.
DNA replication is carried out by a molecular machine called the replisome that pulls apart the double helix and makes an exact copy of each strand. In this visualization, we're going to examine the mechanism for copying DNA. The enzyme DNA polymerase synthesizes DNA molecules, using the original molecule as a template for the production of a complementary strand. The genetic code in the template strand is paired to free-floating bases, matching cytosine to guanine and adenine to thymine. DNA polymerase creates an exact copy of your DNA code, making less than one mistake in a billion bases.
One mistake in a billion bases. But if Pol E is mutated, then many, many mistakes are made. However, the numerous mutations means that the cell metabolism doesn't work well, and it attracts lymphocytes from the immune system to kill the cancer. So it's like scoring an own goal if your DNA polymerase doesn't work. And this is why these cancers do much better. So what are the implications for lab testing? Well, the first thing that we actually need to do is identify these Pol E abnormal cancers, because some of them will be P53 positive. So we don't do that first. In an ideal world, what would happen is endometrial cancers or curettings would come in, and we would identify them on the H&E and issue a report that says it's endometrial cancer. And then in week 2, we would do the immunohistochemistry for DNA mismatch repair and P53, and at the same time, send it off for Pol E genomic testing on every cancer. Great. Except that costs money. So in the real world, we're only going to test cancers where knowing the Pol E status will make a difference to treatment. So what happens with these Pol E cancers? They look really, really bad, but behave well. So that means if we identify the Pol E mutation, then we can de-escalate treatment. These women do not need loads of radiation and chemotherapy because they're going to do well anyway. And we will save money by testing because these women will not use up radiation and expensive chemotherapy treatments. So here we go. This is what I think we should do to move into the molecular era. So I think we should look at the curettings as they come through into the lab, and then identify the women who are in danger of overtreatment. So these are going to be cancers that are high grade, either, clear cell, serous, endometrial grade 3. And we will weed out those ones that do not need extra testing. That do not need extra treatment. Now, if the cancers are high stage, in other words, they've spread everywhere, they're going to need extra treatment anyway. So we're just going to test the high grade, low stage treatments, the stage 1 where it's still confined to the uterus. And we'll go to them, a Pol E, P53, DNA mismatch repair, and ER. Now, if the endometrial cancer is low grade, doesn't look bad, we're not going to treat it anyway, then we won't be over-treating them. So they don't need the extra Pol E test. And if it's high grade and high stage, well, we're going to be giving them lots of treatment no matter what the Pol E says. So they don't need testing. So they just go for P53 mismatch repair and ER. So by doing that, we can reduce the number of cancers that have Pol E testing just to the ones where it will actually make a difference. And we can find those Pol E cancers that do well and remove their overtreatment. So how do we test for Pol E? So fortunately, Pol E can be tested on formalin-fixed paraffin-embedded tissue. And at the moment, what we can do is send sections on slides to Sonic Genetics, where they do a focused gene panel in Australia, and it costs $350. The good news is that we can do this. It's just a molecular panel. We do them all the time. If we do it, it will save money because less people get expensive treatment. And at the moment, we are writing a business case to do it in Wellington. Your lab could do it too. About 10% of endometrial cancers will need to be tested, possibly up to 20, at the most 120 per year in New Zealand. And yeah, then we can implement the new molecular classification of endometrial cancers. So that's all I have to say today. It is the end. Thank you very much for listening to me talk. Goodbye.